Hey everybody, here we go. We're going to start into the first part of electricity and magnetism tonight, which is chapter 15 in our textbook, the chapter on electrostatics or static electricity. This really isn't officially a part of our course. It's largely a review of grade 9, but there's a couple of new concepts in here that I think are important before we move on to starting our new chapter 16 on electric current on Monday. Right, so congratulations on surviving and getting through our fourth unit on electricity, on energy, work, power, and energy. That's a big unit, a lot to be covered, but you've done a lot, you've learned a lot, and there's some really good marks from what I'm seeing on that test today, even though I haven't had a chance to look at it yet. Not officially look at it anyway. Okay, so chapter 15, electrostatics. Statics means stationary, or in French, stationnement, which means parked. So it's talking about electricity or electric charge, which is at rest. It's not going anywhere. It builds up on an object and it stays there. Right? It's delivered to an object and it stays there. Now, in order to understand static electricity, we know about atomic structure like nobody's business at this point in time. After having done our nuclear test earlier today, we know all about the nucleus and its protons and neutrons. We're going to spend time in this unit looking at electrons. Right? Again, remember, chemistry for the most part is electron science. It's all about how electrons are shared, electrons are transferred, electrons. Protons and neutrons are just kind of the substance, right? Unless we're talking nuclear reactions, which are very, very rare, right? We don't see nuclear reactions in this world on any kind of regular basis. Most of what happens in our lives are just the general non-nuclear reactions, just chemical reactions involving bond breaking, bond forming, bond sharing, bond rearrangement, right? So all that involves electrons. So as we move forward here, we've got to look at the fact that when we look at matter, matter has the ability to become charged, right? Which is part of what static electricity is all about. It's objects becoming charged, and they become charged either by gaining electrons or by losing electrons. Right? Gaining electrons or losing electrons. If they gain electrons, obviously it's going to make them negative. And if they lose electrons, that will leave them positive, because they've lost some of their electrons. Means there are more protons left than electrons, because matter typically has an equal number of protons and electrons, pluses and minuses, positive and negative charge. If I lose some of my negative charge, that leaves me with a surplus of positive, right? And that will leave me with positive charge. So notice things don't become positive by gaining pluses. Things become positive by losing their negatives. Once they become charged, this brings us to our law of electric charges that we all know, indicating that opposite charges will always attract, like charges will always repel, and that if I have an object that's neutral, it will be attracted to charged objects. Neutral is attracted to positive objects, neutral is attracted to negative objects. So, how do I make an object charged? Well, there's three ways to make the object charged. The first is the one that I think is the most common in terms of our understanding of static electricity, and that is by friction. Okay, so in friction, whenever I rub two different types of matter, so as I'm sitting here doing my note, pretty soon you'll hear a buzzer go. That'll be my dryer in the room next door, telling me that my laundry's done. What's going on is clothes in the dryer are tumbling over top of each other, and as they're doing that, some of the clothes contain cotton, some of them contain wool, some probably contain some polyester and some rayon and some dacron and some all the different polymers that we talked about in organic chemistry. They're all in there and they're tumbling over each other, and what we know is when two different types of matter rub together, electrons are transferred. Right? They're transferred from one of the types of material to the other type of material. Now, they will always basically travel in that same direction. If I rub one type of material with another type of material, and it makes object A becomes positive. If I was to come back and do it again tomorrow, A would become positive again. And if I was to do it again the next day, A would become positive. So there is a pattern, right, which tells me that electrons always move in one direction, and they move in the direction of the object that has the strongest attraction for those electrons. So when I rub the two types of matter together, electrons will leave the matter that has the weakest hold on their electrons, and then we use the electrostatic series over here to show us which objects have the highest attraction for electrons and which objects have the weakest attraction for electrons. So cat's fur, or our hair even, has a very weak attraction for electrons. Things like rubber in a balloon have a very high attraction for electrons, so you rub the balloon in your hair and your balloon becomes quite negative. It will steal electrons from your head, right, and it will make your balloon negative. And then, according to our law of electrostatics, the negative balloon is attracted to the neutral wall. So the electrostatic series here, just like our periodic table, is a series that we never memorize. We just use it. We have it handy, and it's always there when we're doing electrostatics. Now, it says, yeah, if I've got a rubber balloon and I rub it on my woolen sweater, again, the rubber and the wool, right, the rubber here, which is further down the list, right, will steal electrons from the wool, and the rubber will become negative, and the wool will become positive. Okay, so electrostatics. The second way of an object becoming charged is if it comes in contact with a charged object. So if I have an object like that wool that we just charged up there, and I touch it to a neutral object, it will make that object negative. Positive, because it's positive. If I take the rubber balloon and touch the rubber balloon to a neutral object, it will make the neutral object negative. Right? So once your object is charged, right, it can now transfer that charge, right, to a neutral object when it comes in contact with that object. Right? So like I said, if the negative balloon touches a neutral object, the electrons will leave the balloon until the two are the same charge. Right? As soon as, it's just like heat exchange. Remember, the hot thing will lose heat to the cold thing. The cold thing will absorb the heat from the hot thing until they're both the same final temperature. The same thing here. The negative rubber balloon will transfer electrons to the neutral object until they have an equal amount of charge. Now, if I look at what happens if the wool from above, which is positive up here, right, the wool is positive, and I touch it to a neutral object, what it's going to do is it's going to steal electrons from the neutral object. Right? Again, electrons will continue to flow from the neutral to the positive wool until they're both the same charge again. Right? So the whole idea here is transfer will happen, just like heat, until there's equivalence on both sides. Okay, my third way of charging an object is by induction. Induction is a way of basically creating a charge in a neutral object by bringing a charged object close but not touching. Okay, so when we're charging by induction here, I'm going to bring a charged object near but not touching a neutral object. And what happens is the electrons that are in that neutral object will move. Right? They will move because of the electric charge that is nearby. If the electric charge that's brought nearby is negative, like the negative rubber, and I bring it close to a wall, then what's going to happen is the electrons that are in the wall don't like the negative charge on the rubber balloon, and they will migrate as far as they can deeper into the wall. Now, they can't travel because the wall is not a great conductor of electricity, but they've got some ability to get pushed deeper into the wall. And what happens is that leaves the front of the wall slightly positive. It's positive because, again, the negative balloon pushed the negative electrons on the surface of the wall deeper into the wall, making the surface of the wall positive. And now my positive wall is attracted to the negative balloon. That's why neutral objects are attracted to charged objects. What about the opposite situation? If I bring that positive wool close to that same neutral wall, the electrons that are in the wall at the surface of the wall are going to be attracted to that positive charge on the wool. And what that's going to do is they're going to migrate. They're going to move to the surface, and that will make the surface of the wall negative. Now that positive wool will attract the negative wall. As soon as I take the wool or the rubber away from the balloon, that induced charge separation, which is what it's called, I'm going to write that down here. Induced charge separation. Now, that word induction, we're going to come back to that again in our final chapter of this course. Induction happens when something is pushed, something is forced. Again, when a mom is pregnant and she's at her term and 9 months, and the doctor says at 3 months, "Oh, congratulations, you are pregnant, you're going to have a baby." And the patient says, "When am I going to have this baby, doc?" And doctor says, March 3rd. Say, okay, March 3rd, we're going to plan for March 3rd. Right? About 6 months from now, on March 3rd, we're going to have our baby. And the next thing you know, March 3rd rolls around and mom is huge. No baby. March 4th, no baby. Mom's getting bigger. Right? March 5th, March 6th. Been to see the doctor. Doc, how am I doing? Good. Your blood pressure's good. The baby's well. You're a couple of days overdue. By the 12th, if you haven't had your baby, we're going to induce you. Right? Induce means we're going to give the body hormones that will trick the body into thinking that it's time to deliver the baby instead of the baby sending the message to the mom. We'll artificially force that baby to be delivered. Right? So that's induction. So when we force something to happen, what happens here is my neutral wall. Here's the wall with pluses and minuses, pluses and minuses, pluses and minuses. And if I bring a large negative charge towards it, I'm going to induce a charge separation. So the negatives will go deeper in the wall, leaving the front of the wall positive. The wall is still neutral. It still has the same number of negatives and positives, but I've caused the charge to separate. I have induced a charge separation in the wall. Right, the same thing if I bring a positive object towards the neutral wall. Electrons that are deeper in the wall will see it. They will move up towards the front, leaving the inside of the wall a bit more positive, but the surface more negative, and that makes one way of inducing a charge, even though it's just a temporary effect, right? Until the inducing charge is gone. All right, let's keep going. We're almost done here. Electrical discharge. As soon as that charge builds up on an object, if it builds up enough, it gets really unstable. It does not want to stay there. Right? All that charge will repel all the rest of the same charge, so that buildup of charge is really not happy on the object. Right? That charge is repelling the rest of the charge. That's wherever it is, if it's all positive or if it's all negative. So let's say if it's all negative, object has a large amount of negative charge. If there's enough of a repulsion, enough of a push, I can force those electrons to go through mid-air, right, and hit something else that will accept those electrons. Often it's the ground. I'd say most of the times it's the ground, and the ground could be me, which is standing on the floor. It could be so I walk across, I reach for the door handle, and I get a shock. Okay, what happened? There was a buildup of electric charge on either the door handle or on me, probably on me from walking across the carpet with my socks on. I end up with some friction, which created a charge on me, and as I reach for the door handle, it wants to leave me and go into something else that will accept the charge, which is that door handle. All right, so that's electrical discharge. The same thing happens in lightning. If the object is has a large amount of positive charge, so if it's got negative charge, electrons want to get away. If I have a lot of positive charge and I reach for the door handle, electrons that are in the door handle are attracted to my positive fingers, and as my fingers get close enough, they will jump through space and cause my fingers to accept the electrons and create a small shock for me. Right? So there is our electrical discharge. The same thing happens in lightning when I end up with a large amount of electric charge building up in the clouds. Right? Oh, there's my timer telling me that my clothes are done building up static charge. And what happens is, as they are up in the clouds, it induces a charge separation on the surface of the planet. And because of that, the charge can jump between the planet and the cloud. Right? So there is lightning, and it's exactly the same thing as we were just talking about with electrical discharge and that door handle. And I would have loved to have been able to get the Van de Graaff generator out and do a little bit of shocking in class. But again, with the Van de Graaff generator, the big ball, hopefully you used it in grade 9. If you take grade 12, just remind Mrs. Bateman if she's teaching it, or remind me if I'm teaching grade 12, that you didn't get to do this this year, and you want to get the Van de Graaff generator out and do some shocking things. All right, and again, what happens there is we build up a large amount of electric charge on the sphere by friction, and then that electric charge, those electrons do not want to stay there. They're desperate to get off, and when my hand gets a little bit close to it, it will jump from the sphere to my finger, right, causing quite an intensely, almost painful reaction in my body. But those electrons want to jump. They want to get out of there. We talked about, again in grade 9, 2 different types of materials, those that conduct electricity and those that do not conduct electricity. Right, our conductors are typically metals. Right, our metals are typical good conductors of electricity because metals typically have a weak hold on their electrons. What that means is if I push an electron into one side of an electric wire, of a copper wire, it will push the electron that's in front of it in the wire deeper into the wire, which will push the one that's ahead of it deeper into the wire, which will cause the one ahead of it further and further and further until I get to the far end of the wire, and then the electron will get bumped out the end. So as I force an electron into one end, it is forcing an electron out the far end. Right? That's how our conductors work. In an insulator, like the plastic or rubber that coats electrical wires, electrons can travel quite freely through the materials, through the metals that are inside the wires. But because those insulators hold onto their electrons so tightly, they will not allow anything to push electrons into them, which means no electrons can move through them. Okay, so here's where we get into what we need for this course, right? And it's how do we measure the amount of charge on an object? Now, the charge is basically caused by a surplus of electrons or a surplus of protons, a deficiency of electrons. So, if we just make things really simple for a minute, if I look at, so we're measuring charge, if an object gains an electron, then it has some negative charge, right? So if an object picks up an electron, it has a negative charge. If it picks up 10 electrons, it has 10 times as much a negative charge. If it has 1,000 electrons, it'll have 1,000 times of that electric charge. Now, that charge on an electron, again, remember here in 2020, we've never seen an electron. We've never touched an electron on its own. We can't, they're just too small to even mention, let alone do anything with. So we can't really measure the amount of electricity or charge that builds up using any kind of meter or device, right? That just can't happen because the electron is too small. But if I want to measure a standard unit of electrons, so again, if I get a job working at No Frills or Fortino's, and my job for today is to refill the shelf that has flour on it, I'm going to put 10 kg bags of flour on the shelf. And maybe I'm going to put 50 of these bags on the shelf. And my boss will say, what did you do? I'll say, I put 50 bags of flour on the shelf. Now, recognize that each bag contains billions or trillions of grains of flour. A single grain of flour is invisible, right? You wouldn't even know it was there if it landed on if it was on your arm, you wouldn't even see it. If it was on the counter, you wouldn't see it because it's too small to see, right? Maybe you might possibly be, but it's really, really small. So to try and measure grains of flour makes 0 sense, right? No one's going to go into the store to buy, oh, I need 75 million grains of flour to make this loaf of bread. Again, useless. So we need to measure useful quantities. And a French chemist, physicist named Coulomb did a lot of early work with electricity and their understanding of electrons. So the unit that we use to measure a standard amount of electricity or electric charge is a coulomb of charge. We got a newton of force, we've got a watt of power, we have a coulomb of charge. It's a quantity of charge. Now, just like I know that a newton is the amount of force required to accelerate 1 kilogram of matter by 1 meter per second squared of acceleration, I know exactly how much a coulomb is too. And I can't really describe it to you unless I say, well, the coulomb itself represents a fixed number of electrons or of charge, because remember, the charge on an electron is the same as the charge on a proton, except it's the opposite charge, right? The charge on an electron and proton are exactly the same quantity, but they're opposite in charge. So in grade 12 physics, you get to do an experiment, probably as a gizmo or maybe as a PhET, as a physics application, and it's called Millikan's oil drop experiment. Oh, that should say SPH for you in physics, not chemistry. Okay, you'll talk about Robert Millikan's experiment, and you will spend some time analyzing the data from Robert Millikan's experiment. And in that experiment, Millikan basically was able to determine the amount of charge on an electron. This was done a long time ago. I don't know what year Robert Millikan did this. I should probably know. But he was able to quantify or measure or determine the amount of electric charge on one electron, which again has to be the same amount of charge that's on a proton also. But again, it's negative charge versus the proton's positive charge. That charge, because it's on the fundamental building block of matter, which are protons and electrons and neutrons, that charge is called the elementary charge. It's the fundamental charge, the standard charge that's used when we talk about atomic charge. We talk about ions, charge +1, +2, -1, -2. Right, that has to do with the number of electrons. And again, we can measure the charge on an ion if I know how much charge is on an electron. So the symbol that was used for the elementary charge is a little e, and it's usually written as an italicized e. This was italicized when I first made my note, but I think in transferring it to Notability, I've lost my italicized e. So the symbol is little e, and the number that is the charge on an electron, as determined by Robert Millikan in his oil drop experiment, is 1.602 times 10 to the negative 19 coulombs. It was a pretty small number. Right? Again, think about the mass of that grain of flour versus the 10 kg bag. Right? It's pretty small. So it's the same thing here. So now that I know from Robert Millikan what the charge is on an electron, if I know how many electrons are on an object, either as surplus electrons or deficiency of electrons, and I know what the charge is on an electron, then I can figure out the quantity of charge that's on that object measured in coulombs. Now, notice here that they're using the same symbol that we use for heat, which is Q. I'm not sure why they use Q for both. I'm not sure why they use Q for heat, because historically a lot of the older books used to use E with a little h beside it for heat or thermal energy. But a lot of the newer books are using Q for heat also. So our Q in this chapter is the quantity of electric charge, and it is based upon the number of electrons that are plus or minus, that are additional or deficient, times the charge of an electron. So if an object has 10 surplus electrons, it will have a charge of, I'll take my 10 times the 1.602 times 10 to the negative 19, which makes 1.602 times 10 to the negative 18. That'll be then coulombs, and it'll be negative because it is a negative charge. So I'm just going to stop right there, and that will finish our note, and our whole chapter 15 is there in that short note. I'm going to ask you to look at the one example that they've done for you in the text. I'm not going to do it because it's just Q equals NE. And then there's 5 quick questions on page 540. And I'm going to leave you just one page to read on your own in the textbook, and that's page 534. There's a table on that page. It takes up the whole page, and it talks about applications of electrostatic force. Most people think of static electricity as a bad thing. Causes shocks, causes lightning, causes fires, but we have lots and lots of applications for electrostatic forces and electrostatics in general. Okay, so I'm going to finish there, and we will start next week into chapter 16 on electric current, and hopefully you will find this, again, very different than what we've been doing, but again, a very interesting unit, and lots and lots and lots and lots of opportunities. Electrical technicians, electricians, electrical engineering technicians and technologists, electrical engineers, just on and on and on, all the different possibilities. And again, you would have seen that if you, depending on what you did with your career assignment.